Okay. Uh, well, here we have Dr. Wolf. He is the director of the Rice Emerging Scholars Program, and that's how I know Dr. Wolf personally. And he's here to talk to us about what it's like to be a professional mathematician and college professor. Dr. Wolf, tell us a little bit about yourself and the kind of work that you do.
Okay. Um, let's see. About myself. That caught me unprepared. So here I am. I got my PhD about 35 years ago now in California, and I had a pretty routine, pretty standard career as an academic. I first did an instructorship in New England, and then I came to Rice to have a tenure track job as a professor in 1988, a long time ago. Probably no one listening to this was born then, but I came to Rice because my wife was interested in space and she wanted to go to graduate school at Rice, and so that's why we came here, and so we've been here ever since. So I'm a professor. A professor has many aspects to it. You can, as you imagine, I teach. So I teach classes. That's probably how you think of professors, sitting in front of a room lecturing, and I do that. Mostly that sort of class is usually for undergraduates. I also teach more informal classes for graduate students. And then I have my own PhD students, students studying for their PhD who work with me on a research problem. And that's a very one-on-one sort of discussion. So I tend to meet with each of those for about a couple hours every week. And it's just chatting often over coffee about what they are working on. At the same time, I do many other things. So I am a research mathematician. So that's going to maybe strike some in the audience, say, as a little strange. I mean, research in mathematics, I thought research was biology or chemistry or engineering, but we turns out there's also research problems in mathematics, and people like me try to solve them. And it's somewhat invisible, but it's very much like research in other fields. There are phenomena in mathematics we don't understand. And so we apply the techniques that we've built up so far to understand those problems. Sometimes we have to invent new techniques. And when we take those old techniques and new techniques and we solve the problem, and immediately after you solve one problem, you have 5 more to solve. So it's very much like biology or chemistry or physics, except we don't we don't inject animals with things and see what happens. We don't shine lasers at little bits of material and see what happens. And then when we see what happens, we ask the next question. Here, these are mathematical phenomena. And so very much what I do is like what you guys do on math homework, right? Except, math homework, you have a problem, you try to solve it. You don't know how to solve it when you start, and you take what you've learned and try to solve it. And I do the same thing. Then you can sort of imagine the difference between me and you is that my problems have not been solved before, but it's very much like what you would do, because imagine you're the first person who ever came across that problem on your math homework. What do you do? So it's some sense I am just doing the same sort of thing that that you do on your math homework every night, but I do it. My problems tend to take longer to solve. Does that help?
Yeah, it does. It does. Kind of opens up what people may not know about, like, what does it mean to be a mathematician? Like, yeah, it is research, and it's hard research.
Yep. I don't know that it's harder or easier than the other sorts of research, but it's important. Everything that you learn in math was found by humans doing the same sort of thing that I do some years ago. The calculus that folks take late in high school or early in college that is responsible for so much in as an effect in the world, and it was made up by human beings in the 17th century. They moved beyond the Greeks, and the Greek math was all in terms of straight lines. And then there were some notions in the 15th century or so about how algebraic expressions, which were invented in the Arab world, and studied the Arab world in other places, and in East Asia as well, and how they had a way of turning those algebraic expressions, x squared plus 5x plus 7, into some curve. And so suddenly the Greeks, the Greek straight line geometry became useless, or not well adapted to these new pictures of curves. And what Newton and Leibniz and folks coming immediately after that did was to create a mathematics that described how these curves changed in time. And then this had a tremendous effect on the world in a couple of ways. I'll be very provocative now. So certainly we all know how the effect on science. And so Newton starts describing how planets move around, and we describe mechanical processes. A lot of the physics that you guys study late in high school and early in college is based on the sort of Newtonian mechanics and stuff that came later. And of course, electricity and magnetism grew out of calculus as well. So all the phenomena that we understand, and so therefore all the machines that get built come from this human development of creating the derivative and the integral and the fundamental theorem of calculus for those who do that. I don't know if those were, I don't know your audience if those words are familiar, but these are basic topics that get done in late in high school and early in college. And the other aspect of this that a very profound effect, I think, was that Newton, through the calculus and through physics, which were sort of intertwined at the time, could describe the motion of planets. And so I'm attributing this to Newton. That's a bit of a cartoon that goes further than that. But so a human being, through their mind, could predict the movements in the heavens. A common person, had the power to understand why things were happening. And so this is a profound change to the way humans thought about the world they lived in. Because before this, stuff just happened. People got sick, the stars moved, and it was, the only way to understand it was through deities or through kings. And now a common person could describe it. And so the sort of change in the point of view that gets attached to human beings like me, like physicists, like others, biologists, engineers, being able to control nature through their minds and through their equations. The effect this has on society and in the hierarchies in society, I think, can't really be underestimated. And it's something we sort of take for granted. But if you want to think about humans doing math, you need to think about that sort of effect as well.
Yeah, I would say, like, what kind of a person would it take to be successful in like the kind of areas that you're in, like teaching or even doing research in math? Like, what kind of person would do well in something like this?
Oh, you just gotta like it. Or, I mean, it's actually, for me personally, I think it's the sort of thing I struggled with the most when I was in school. Other things seemed easier, and this just seemed like to have a certain depth and richness to it, and I was just attracted to that. It was just hard. It was hard for me, and so that made it interesting. I should say that, it's not like I had a plan. Like I was going to be a research mathematician, at age 7, I started preparing for that. I just, I like doing math, so I kept taking more math courses. And after I took enough and did enough, then I liked the problems got harder and more involved. And so eventually there were problems that were new. And so I solved some of those and I got a degree, and then I like doing it still. I like solving problems of this type. And I just ended up in this career, and it's actually a great career because I get to think about math, which is fun for me. Some people listening to me might like thinking about biology, and that's fun. I've known friends who like to stare at objects in the room and imagine their chemical composition. And if that's fun for you, go do that. I have friends who love to build things and to make things and to like imagine a new device and how it can affect the world. And if that you like that, just keep doing it. I never had much of a long-term plan. I don't know, long-term plans are really that useful. If you like solving problems, then then keep solving problems, and the problems will get more complex, and then you'll have a career because that's valuable to be able to solve a problem. And problems come in all stripes, and it's useful to have people that can solve all different types of problems. So I would say this, that I'm trying to think of a good answer to your question, that it's worth doing difficult things. If you find something difficult, go do it, and just realize that the world appreciates people who can do difficult things. So do something that's difficult for you that you like, and the career will follow.
Yeah, and it's really funny because this is like a good segue that you might have already answered, but what's one piece of advice that you would give anybody still trying to decide what type of major or career pathway that they're interested in?
Well, I think I have. I think I would say go do something that you like. You're gonna spend a long time doing it, and the mistake. So maybe I'll turn your question around. So I think that's it. Go do something you like. If it's difficult, people will appreciate that you can do difficult things, and the career will follow. So start with what you like, and then the career happens. If you try to game the system, you try to guess, like in 25 years, what will the world want? You might get that right, and you might get that wrong. But if you're trying to do something, if you end up doing something you don't like because you think it will be useful in the 5 or 10 or 15 years it takes you to get to where your career starts, that's a lot of time to put in doing something you don't really like. So, and you might be wrong. Fields change a lot. If the iPhone, which we think of now as something that they must have been using back when dinosaurs walked the earth, is from 2007. The notion of big data. I'm so old. I was around when big data started. So big data, I think that word is 2003, 2004, which sounds like really old to you, Benjamin. But when you're 3.5 times your age, like I am, it's not that long ago. It is a blink of an eye. And in some sense, before big data came around, there was this very sleepy profession called statistics. And people went into statistics because somehow they liked thinking about data, but it was a very small field. And then computer science came along, and computers came along and started generating these gigabytes and terabytes of data about interesting things, about the body's reaction to disease or to cancer rates in communities, cross-referenced by hundreds or thousands of variables. And it was too much for for humans to do on their own, they needed to do something mechanical. And that was a very new field in around like just 15 years ago. It was the birth of a new field. And for people, and there were some people around who actually liked statistics. They'd gone into statistics, they liked it. And suddenly they're the most important scholars and thinkers around because there's this problem around that's really interesting. They didn't get into it because they saw that coming. I know those people. I've talked to those people. I know they didn't get into it for that reason, but they were there. And so that's what happens with the way ideas course their way through society and through history. So my advice is first do something you like. It should be difficult. That's helpful. And then people will appreciate that you can do difficult things, and you might get lucky because even if you're working in a field that doesn't seem that appreciated, in some sense, a small village in the landscape of ideas, every once in a while the circus comes to town, and then there you are in the middle of something really big. So.
Yeah, well, that's really fascinating. Thanks for telling this to us, Dr. Wolf, and it was really great hearing from you.
Great. Well, thanks a lot. I hope this helps.
Yeah, it does. Thank you.
Okay.